Hello again. How are you? I'm fine. It's time for 6.3, vectors in the plane. So we're going to talk about what a vector is first. Going to define a vector. Always have to define the things we're talking about, whether in math or in life, in a conversation, whenever, you need to just define what you're talking about first. After you define the vector, you can find something called the component form of the vector. Okay. And in this, we're going to compare vectors to each other, talk about how they compare to each other. And then after we talk about that for a bit, we're going to perform vector operations, make vectors interact with each other. After we do all that, we're going to find something called the unit vector. It's a special form of the vector that we're talking about. If we're given a vector, we can find it. It's a unit vector. Once we talk about unit vectors, we're going to talk about linear combinations of those unit vectors. Okay, so let's get started defining what a vector is. A vector is a very simple thing. If I want to tell you what a vector is, all I have to tell you is that it has a magnitude, a size, and the second thing is that it has a direction. Okay, so if I can tell you something is this big and it's pointing in that direction, I've told you about a vector. Okay, so let's look at this pen. This could be a vector. If I talk about, I have to give it some kind of reference, like I would have to give it a scale. So let's say it's 5 long. Okay, it could just as easily be 50,000 long, but it's just 5. We'll say. So another vector that goes down there could be compared to that length. So then let's also use as reference the size of this paper. Okay, so I could say that its magnitude, its length is 5, and its direction is it goes up so much and it goes over so much. Okay, that would be a way to represent its direction. I could also say that compared to this horizontal, it is pointing, looks like maybe 35, 40 degrees, probably more like 30 degrees. But, you get the idea. It's magnitude and its direction. Okay, so if one vector has a magnitude and direction, then how do we compare two vectors? How would they be equal? Well, there's only two things that define a vector, a magnitude and a direction. So if two vectors have the same two things equal to each other, then they must be equal vectors. If they have the same magnitude and the same direction, they're equal vectors. So let's look at number 1 in the homework set, and we'll also talk about some things, some ways that we refer to vectors and talk about them. So I've just drawn a point, and we'll talk about this point. This point, I'm going to start drawing the vector at this point. So this is called the initial point. Okay, we'll call this point P. I'm going to keep drawing this, and it's going to go and stop at this point. It terminates here, so it's called the terminal point. Initial point, terminal point. You can tell the terminal point because it has the arrow. It points this direction. It must start here and end here. Okay, so this one they call U. So here's another thing about vectors. They talk about them with lowercase letters, and those lowercase letters are bold letters. It's a little hard to do as I'm writing. It's easier to distinguish when it's typed out, but try to write them bold. Okay, this terminal point we'll call Q, right? P and then Q. So P comes first in the alphabet and Q comes next. That's how you can remember initial terminal. Okay, two ways we can write a vector. If I was going to write a vector, I was going to write to you in a letter and send it in the mail and talk about this vector and all the things we did this summer, I would say this vector, PQ, with an arrow over it like this. Now the arrow just has like one little thing, one side of the arrowhead, not both. Okay, so this is equal to also saying, this is like his nickname. This is what I call him when we're out and about. I just call him, hey, you. So this is the vector U. It's also called the vector PQ. And that's how we talk about vectors. Okay, so let's talk about where these points actually are on the plane. This one's at 2, 4. This one is at 6, 5. Okay, so there's the vector. Here's another vector. It starts here. Its initial point is at 0, 0, 0, 0. Its terminal point is over here at 4, 1. And this one is called V. Look at that. Okay. So now we're going to verify, these problems say verify that these two things are equal. These two vectors are equal to each other. What do we have to show? Again, that they have the same two components, the same magnitude and the same direction. So first, let's find the direction. I think it's a little simpler. So the direction of this guy right here is what we'll find first. We'll find the magnitude of it, and then we'll find those two things for this vector. So the direction, that's the same as the, we'll use the slope then of this line. So let's say the direction, d, is equal to, well, just the change in y over the change in x. 5 minus 4 over 6 minus 2, right? We need to do that in the right order. If we use this one first, then 5 and 6 need to be the first numbers, and then we subtract only numbers from here. So the y values and the x values, basic slope stuff. So this is 1 over 4. The slope is 1 over 4. The direction is 1 over 4. Okay? Now, some new notation that I'm going to introduce here. The magnitude, the length of u is represented this way. 2 vertical lines, like this. Then the name of the vector, and then 2 more vertical lines. This is called the magnitude of u, the length, the size of u. How do we find that? Well, since it's a vector on the plane, it's a directed line segment, then its magnitude can be defined by the distance formula. This follows from the Pythagorean theorem, so I would just do 5 minus 4 squared plus 6 minus 2 squared equals, well, this 5 minus 4 would just be 1. I square that, I get 1. 6 minus 2 would be 4. 4 squared would be 16. So this is 16. We just said this was 1. 16 plus 1, that gives me the square root of 17. There it is. It's not a fantastic number, but it is a number, and it is something we could compare another number to. Okay, let's talk about v, all the things about v that we want to know. So its direction is going to be its slope. It's going to be 1 minus 0 over 4 minus 0, that's 1/4. All right, so fantastic. Half of this thing is checked out. Now we need to find the magnitude of v. Okay, that's going to use the distance formula again, the square root of, now this time, 1 minus 0 squared plus 4 minus 0 squared, 4 squared, 16, 1 squared, 1, 16 plus 1, square root of 17. Happy day. They are equal. The magnitudes are equal, the slope, the direction, they're equal, so there we are, 2 equal vectors, right there in front of us. Okay, so now that we know how 2 vectors can be equal to each other, we're going to talk about a special kind of form of a vector. Okay, so let's say I draw a vector right here, and I always will start this kind of a vector at 0, 0. We just are going to assume that this vector starts at 0, 0. Okay, if we assume that these vectors, these component vectors, start at 0, 0. Then we can talk about them in a simple way. Okay, so say this guy points this direction, and let's say that it goes to 4, 3. This is where this one ends. Okay, this is u. Okay, so if we agree that it starts at 0, 0, then all I really need to tell you about this is that it's at 4, 3. This would uniquely represent this vector. I could tell you any point on the plane, and the way that you know what that vector looks like is you just start at 0, 0 always and go to that point. You can see that that would uniquely represent any vector of that form, of component form. Okay, so here's how I would, rather than having to say a bunch of words, I'm just going to use different brackets. Using these pointy brackets tells you the component form of this vector. I'm going to tell you that this vector is 4, 3. With pointy brackets tells you that you don't need to know the initial point of this one because you can assume that since it has pointy brackets, the initial point is at 0, 0. What's so great, fantastic, and wonderful about component form? Well, one of the things is that it makes, let's say, finding the direction really easy. Because what is going to be the slope of this line? Well, it's going to be up 3 and over 4. That's going to be true of anything that I tell you in component form. It's just going to be the y value over the x value. So 3 over 4, I'm done. Direction is done. Okay. Now let's talk about the magnitude. Well, the magnitude, okay, let's use the distance formula. It's the square root of 3 minus 0 squared plus 4 minus 0 squared. That's equal to 16 plus 9, that's 25, the square root of 25, and that is 5. All right. But really, was it necessary to write all this much? No, because if you look at this as like a triangle, that's what the distance formula is all about, and I want to find this distance, the hypotenuse of this right triangle, well, it's just a squared plus b squared equals c squared. Okay? So all I need to do is just take these two guys here, square them both, done. I found it. Okay, so when it's in component form, all I need to do to find the magnitude is just that. I'm done. So distance, magnitude, done. Okay, so now we're going to talk about how to take a given vector and find its component form. To convert it to a form where we can assume its initial point is at 0, 0, and we don't even have to worry about it. So let's say that we have a vector in the plane. Let's just look at a picture of a vector. Okay, so here is a vector here, like this. Okay, I'm going to put some numbers here in a minute, but let's just look at it. I want to move this point to here, and then keep the same direction so that this point winds up where it would if I could just slide this down over here. Okay, so a simple way to look at it is first, I could go this way or I could go this way, but first I'll say I want to slide this horizontally until it touches the y-axis. Once I've done that, once I've slid the whole thing over to here so it's touching the y-axis and it's pointing in the same direction, I want to then take it and slide it down here, right? Okay, so it seems like a simple enough operation, okay? Which is the equivalent of moving this point this much, as much as I've moved this over, and then moving it down this much as I'm moving this down once I've gotten it over here. So let's look at if this is the point 3, 3, and this is the point 7. That was a tough decision. 5. Okay. So I'm going to move this guy over this way 3, right? Because it's 3 away from the y-axis. I don't want to move it after that. I want to move it down 3 because it's that far away from the x-axis. So I want to move this the same amount, right? So now the order in which I do this, I'm going to subtract, right? I'm going to move this to less than it is. So it's very important that I do this in the right order. That I start with this these coordinates or the values from this coordinate first and subtract the values here because I want to move this stuff this way. Okay, so if I want to move it in the horizontal direction this way to move this point, then I want to move it over 3. I want to take 7 and I want to subtract it 3. Okay, this is going to be the new point, the new terminal point. So 7 minus 3, and then I want to move it, once I moved it to the left enough as much as I need to, then I'm going to move it down as much as I need to. Well, when this point moves over 3, the next goal is to move it down 3 this direction. So then I would take 5 and move it down 3 because of this 3. I kind of apologize for using 3 and 3, but recognize that this 3 goes with this 7 because they're the x's, and this 3 goes with this 5 because they're the y's. So 7 minus 3 is 4, 5 minus 3 is 2. So the component form of this vector would be one that starts here and ends here, starts at 0, 0 and ends at 4, 2. So the component form of this vector would be 4, 2. Okay, well, I need to end this, and I'll see you in the next video.